Institute of Engineering and Technology.
Good morning, students. Today I am going to cover the last part of our discussion in chapter Fourier integral. We already considered first part as general Fourier integral, second part as Fourier cosine integral. Today our focus would be on Fourier sine integral. In my previous video, I already asked you to use the formula of Fourier cosine integral on the given function by taking its nature. Whereas in that video, we have seen that how to fit the general Fourier integral in any situation. Today, I will try to cover the second part as Fourier sine integral directly fitted on the given question using its nature on symmetric range. So, combining both of these videos, it will be clear that in any case or in any situation, if you want to figure out the integral form, which is a Fourier integral form, then the general case is always applicable. But if you just observe the function and if you can check whether it is symmetric and it is even or odd, then you can apply Fourier sine or Fourier cosine integral of them. So let us begin with today's talk, which is Fourier sine integral. Now, in Fourier sine integral, we have seen that in case of Fourier cosine integral, the answer was depending on cos, whereas here Fourier sine integral is obviously depending upon the sine function only. And as I told you earlier also, that if your function is odd by nature, it can be represented by another equivalent odd function. And the most common odd function for the simplicity of calculation which Fourier used was sine function. So we'll see that how to represent f of x as 0 to infinity d omega sine omega x d omega. And here also we'll see that d omega is 2 by pi 0 to infinity f of x sine omega x dx. It is almost similar as Fourier sine series for odd functions on symmetric integral. We are actually using the benefit of range of a omega and b omega, which is always symmetric. So if your function is odd function, you can reduce the range from 0 minus infinity to 0 to infinity, and you get double the value. And accordingly, you can reduce at least one of these two elements, a omega and b omega, while finding the solution using the nature. Okay, now let us begin with example. Using Fourier integral, prove that 0 to infinity 1 minus cos omega pi upon omega into sine omega x d omega is equal to pi by 2 whenever 0 less than or equal to x less than or equal to pi, and 0 whenever x is greater than pi. This is how the given function is defined. Now, solution is by assuming that this is the given function f of x is pi by 2 whenever 0 less than or equal to x less than or equal to pi, and 0 whenever x is greater than pi. So you can see clearly over here that the function is not defined on the whole real line arc. It is only defined on the half part of the positive real line from 0 to infinity. So the Fourier sine integral of this function is given by f of x 0 to infinity d omega sine omega x d omega. So if I consider the formula of d omega, it will be 2 by pi 0 to infinity f of x sine omega x dx. Now, considering the range of function from 0 to pi, my function is pi by 2, and from pi to infinity it is 0. So neglecting the second integral, value of integration will be sine omega x integration from 0 to pi. I am cancelling this 2 by 5 and pi by 2. So what is integration of sine omega x? It is minus cos omega x on omega. Taking the limits 0 to pi will result the value of this b omega into 1 minus cos omega pi upon omega. Now, the Fourier integral or Fourier sine integral is now given by this. And therefore, I can say that the function f of x is pi by 2 whenever 0 less than or equal to x less than or equal to pi, and it is 0 whenever x is greater than 0 is equivalent to this integral. Therefore, this is how you can figure out the solution of any function using Fourier sine integral. Thank you.
LJ Institute of Engineering and Technology.